take your take-home quiz now and not later. So at this point, if you turn it in, if you turn this take-home quiz anytime after now, it'll be late, so make sure you turn it in right away. I will accept them late. There will be a bigger penalty than 10 points. All right, thank you. All right, there's a stack of stuff going around. Make sure you go through the whole stack, pull out anything that is yours, and we are going to continue where we left. Well, no, we're not going to continue. We're going to start something new. Let's talk about our exam. Our exam number 2 is scheduled for next Thursday, a week from today. That'll be the Thursday before spring break. And it'll cover pretty much the techniques of integration, and then the definite integral, which is what we did last time. And then the last topic it's going to cover is this section 6.6, which is called improper integrals. And we're going to get through the first half of improper integrals today. We'll do the second half on Tuesday, but then you're going to be tested on it 48 hours from then. So just be prepared for that pace. I think that you'll find, hopefully, that there's not a whole lot of new things in this in this section as far as integration is concerned. What's new is that we're going to have to do some limits. And so it's going to fall back on your Cal 1 experience. And I think I asked this in the beginning of the semester, maybe not. How many of you are familiar with L'Hopital's rule? Okay, and then who are the people who had not seen L'Hopital's rule? Don't know what I'm talking about. L'Hopital's rule? You're okay? You didn't raise your hand, so. Does it sound familiar to you?
It sounds familiar.
Okay.
Take a shortcut?
Pardon?
Take a shortcut for...
It's a shortcut for taking limits. Well, yeah, I mean, I guess you could call it a shortcut, yes. Okay, so if I start talking about L'Hopital's rule today, and you're not sure what the heck I'm talking about, I recommend that you send me an email. And the best I can do for you is either meet with you in person and kind of show you L'Hopital's rule, or I can point you to some of my online Calculus 1 lecture videos where I cover L'Hopital's rule, and then you can go and watch those if you're interested. All right? But my expectation is that you know how to apply the rules of L'Hopital. All right. How about the homework from last time? Everyone got that email? Okay, I know Canvas was down for a while. So basically that homework assignment was just for you to go back and look at the other problems, that pretty much a lot of the problems you had done prior, earlier in the semester, and go back and now take account for the numbers. All the problems I gave you were odd, which meant that you should be able to check your solution in the back of the book. So just make sure you can get those answers. How does that section impact the exam? Well, now I can give you definite integrals. And when I give you a definite integral, the integrand, you might have to do partial fractions, or you might have to do trig sub, or you might have to do integration by parts. And at the end, you still have to plug in numbers. So it's just one added layer on top of the problem, right? That's all it is. Okay, so today what we're going to do is we're going to investigate what are these things called improper integrals. And I thought I would kind of motivate this with some pictures. So the definite integral is what we talked about last time. And it pretty much said that, or we concluded that if you take a function f and you restrict it, so you cut it off and you just look at a section of it. In this case, we're looking at it on a closed interval. We call this a closed interval. It's the interval a comma b. All right, so it's all the x values between a and b, and we're trying to figure out the area underneath that curve, right? So we were able to determine last class that that area was equal to this integral. And we had the evaluation theorem, which told us that this was equal to capital F of B. Well, hold on. I'll write it the other way. I've got to sneeze. Maybe not. So we had this intermediate step here where we found the antiderivative. We put that bar there. And then we said this was capital F of B minus capital F of A. Right? That was what we did last time. So what we're going to do now is these improper integrals, there's two types of improper integrals. We're going to talk about the first type today, second type on Tuesday, but I'm going to show you both right now, just so you can see what they look like. So the difference between the definite integral like this and the improper integral is easy to show geometrically. Let's say that we take a function and instead of cutting it off on a closed interval AB, right, I start here at A, but let's say I don't want to ever stop. I don't want to like have a right endpoint. So let's say that this function does something, and then let's say that it approaches the x-axis kind of asymptotically, like we had back in college algebra and pre-cal. You had these asymptotes, right? So let's say that our function is going and it's just diving down towards the x-axis without actually ever getting there. Then can we even talk about this area? I mean, the area would be everything. You see, it would start getting pinched off here, but it would never technically get pinched off, right? You're always going to have something down there. Yeah, so how do we represent that as an interval? What we're looking at here is the interval from A to infinity. Make sense? And notation-wise, this would be written integral. As the definite integral, we would go A. Up here, we put infinity, because we don't want to stop. And then f of x dx. And the question is, how do we deal with that? And we'll have a little formula we use, and that'll be it. All right? But do you understand the geometry of the problem? All right, we could change this up a little bit. We could, instead of going from A and going to the right forever, we could do something like this, where we have our function, and this time we stop it at B, and we go this direction forever. So yeah, we're going to go from there all the way up to B and stop. So we're going to write negative infinity, comma, B, bracket on the B. And again, what we'll be looking for there is the area below the function and to the left of B forever.
So we would change the notation of our upper and lower.
Yeah, so all that would change here in our notation would be we start at negative infinity, we stop at B, right? And then f of x dx.
And are those the two types?
No, this is all still within the same type. And let me, next to this, write what those intervals were. The first one was A to infinity, and this one was negative infinity to B. What's the difference between having a bracket versus a parenthesis on an interval?
Included.
Bracket means include the value A. The parenthesis means don't include it. And we always put parenthesis on infinity because infinity is not a number, so we can never include infinity. Just keeps going forever. All right, so these are still within the first type of improper integrals, but there's one last variation. Can you guess what it might be? Go both ways forever, right? Instead of stop, don't stop at all. Nope, because remember the indefinite integral gives us just a function. Definite integrals give us numerical answers, right? So we still have this question that if I don't stop, I go both directions forever, can we assign some value to that? We'll have to see, all right? And now what would the notation for that one be, you think? Just negative infinity here, and f of x dx. And the interval here would look like this. So all three of these are type 1 improper integrals, and we call these improper integrals, all right? But they fall into this category of what we refer to as infinite intervals. So what we have is we have a definite integral, but it's on an infinite interval. Integral, interval, not the same thing, right? This is a definite integral, but our interval is infinite. Make sense? Okay, so that's what we're going to focus on today, but let me show you the other type. The other type that we have is something like this. What if I had a function that behaved like this? Let's say that it had a discontinuity, and specifically, let's say it had a vertical asymptote. So let's say our function did this. Let's just say that this is 1. Let's say this is happening at 2, and then here's 3. Let's say our function came in like this, goes up forever, and let's say on this side it does the same thing, goes up forever. So you cannot plug 2 into this function because the function's undefined there, right? But as you approach from the left, it's headed up to infinity. As you approach from the right, it's headed up to infinity. Then can we actually make sense out of something like this? This would mean we want the area between 1 and 3, right? We want this area here, and we want that area there. And the question is, does that area have a finite value or not? And we'll have to see. Sometimes it will, sometimes it won't. All right? But do you see the difference in the two types? With the type 2, we have discontinuities. We have our function actually blows up here, right? Within the interval, our function is becoming infinite. Do you see that? Within this interval, our function becomes infinite. So the function in the problem is this, right? That's called our integrand. And so this type is called infinite integrands. So those are the two types. Infinite intervals, where your interval is infinite, and then infinite integrands, where you're somewhere, your function, your integrand, within this interval is becoming infinite. All right, let's focus on this one, all right? You get the basic idea, though? Basic concept? Okay. I had to wash this towel over in the sink just a second ago. It smelled like mildew, but now it's really wet, so far it's doing. If you see me doing this, because I have to kind of dry the board off before I write on it. Okay, so pretty much everything I said just now is in the notes for 6.6. So we have this type 1 infinite intervals. Here are the three notations I just gave you: a to infinity, negative infinity to b, or negative infinity to infinity, right? Now, we need to define what they mean. Okay, so if we have an integral that goes from a to infinity, how do we handle it? What we do is we create a limit. And notice what this limit is. We are going to transform the integral back into a definite integral where we're going to be using t instead of b. We're just going to use some dummy variable. And we're going to try and figure out what's going on with this. So we're going to take the antiderivative. We're going to do what you did in your homework, where you find the antiderivative, then you plug in, right? You plug in the top one first, then you plug in the bottom one, you subtract the two. And once we're done doing that, at the end step, we're going to do one additional thing. We're going to let t go to infinity. So that's going to require that we can compute a limit. Understand? then if we want to go the other way, if we want to go from negative infinity to b, again, we're going to rewrite the problem. We're going to replace this lower limit of integration, right? We're going to replace it with t, and then we're going to let that t go to negative infinity. So it's like letting it go out forever that way this time. Does that make sense, the notation? Now, what do you think is going to happen when we have negative infinity and negative infinity to positive infinity? Yeah, I mean, you would hope that you would just do another limit and just let both of these go where they need to go, right? But the technical way we do it is we have to, well, oh, did I get ahead of myself? I did, sorry. Yeah, before I get to that. Remember in Cal 1, when we take limits, limits either exist or they do not exist. Remember that DNE from Cal 1 does not exist? When you take limits, they may not exist. So when we are doing these improper integrals, our answer is either going to be, the limit's either going to exist, which means we're going to get a number, or it's going to not exist, and anytime it doesn't exist, we're going to say divergent. So if the answer goes towards a number, we will say convergent, and we'll write down what the number is. If it does something other than go to a specific number, then we will say that this improper integral is divergent. And we'll need to write that down. All right, it's divergent, or it's convergent, and it converges to wherever. Now, if we have the case where we go from negative infinity to infinity, what we will do is split it into two integrals. Remember, I gave you a property last class that said that if you're trying to integrate, let's say from a to b, right, on some function, that you can pick any point in the middle and then do them separately. So you can do an integral from a to c, then an integral from c to b. Do you remember that property? I had it up here on the board. So because of that, what we're going to do instead is we're going to say, look, if we want to go to negative infinity all the way to infinity this way, then we just need to pick some point in between, and I called it a. And that point that you pick in between is any number you want. Okay, you get to pick any number between negative infinity and infinity. So the number that I like to use, any ideas? 0. 0 is always the cleanest number to plug in. So I'll usually pick 0, but you can always pick 1, or if you want to, you can pick pi. It doesn't matter. You just have to, just remember you have to plug that number into the antiderivative at some point, so why not pick a number that's easy to evaluate? 0 is always easy to plug in, right? All right, so when we have this case, we split it into two. All right, we're going to get to some examples now. But before I do this example, I was hoping that someone would have a problem with this idea that we might actually get an answer, like a numerical answer. So I'll graph this one for you just so we can discuss it. Let's see if anyone has any issues. We are going to go from 1, well, let me show you the graph of this first. The graph of 1 over x squared looks like this. It's kind of like a volcano that's infinite in the middle, just keeps going up forever, it has an asymptote. And then, at 1, it's 1. And we are going to be integrating to the right of 1, yeah? From 1 to infinity. So we want to know the area over here. Let me extend this x-axis. So this continues to go down and down and down and down. And what I'm claiming here is that there's two possibilities. Our answer is either going to be a number or it's going to be divergent, which means that it's not going to be a number. It might become infinite. And for some people that causes a little bit of a problem, a little bit of an issue. So let's say that this turns into a number. Does anyone have a problem with that idea? If I tell you that red area is a number, no one has any issue with that? No? Does this region ever stop?
No.
Okay. Is there always red?
Yeah.
There's always red, right? Now it gets smaller and smaller, and you have to like zoom in and zoom in and zoom in, but you would see red in there, right? Yeah? So if I tell you, just for the sake of telling you, I don't know if this is right, but what if I tell you that that red area is 1? That doesn't bother you? I mean, how can you possibly have a finite area if this region is infinite, right? The region keeps going forever, right? Here's another analogy. Let's say I had a cup that held exactly 1 cup. This is a theoretical cup, okay? So I'm gonna start filling up this.